Welcome back to part 5. In this video we're going to continue with the 16 by 16 LED matrix display, and we're going to make it so that it selects a color based on the count, and the count in this case will be from 0 through to 9. We'll also be looking at how the logic is actually built within the FPGA, both through a logic diagram and the actual lookup table diagram. So far in our previous videos we've created the character ROM, the address counter, and in this one we're going to be creating the color selector. So we're taking the 4 address bits we created in the last video, looking up a color, and that will output, it says /8, it's actually /24 bit, outputting a 24 bit based on the value of the address. And that 24 bit pattern will follow this green, red, blue format that we've got across the bottom here. So this is our code within the EDA playground, and what we have is an input that takes our 4 address bits, 0 through to 9 is our numbers we're counting, and gives us that 24-bit color code. I've then got some constants that are defined as local parameters for my green, blue and red, and noting it's not RGB, it's GRB. And then a register to hold the current color and a way of assigning that register back up to this. Now, we talked in last video that we could actually put a reg on an output. I just prefer doing it with the assign down here. Either way will work though. Okay, so in our always block, we're just doing 3 logical tests. So we're saying always star, I think this is the first time we've used this, will mean this will happen every time. It's not related to a clock pulse or anything, it just instantly happens all the time. So it's a real-time logic that will happen no matter what's changing. So we're comparing if we're greater than or equal to 5 or less than or equal to 9. If that is the case, we'll output a green value. If we're greater than or equal to 3 or less than or equal to 4, we'll output a blue. And if we're greater than or equal to 0 and less than or equal to 2, we're going to output a red. So super simple code. So I'm hoping that you're starting to see the advantage of doing the pre-design in blocks, because it makes your coding so simple. It's not daunting that there's a huge amount going on. It's just lots of little simple areas. Looking at the test bench, all we're going to be doing is sending through the address and receiving the color code back, and every 4 time clocks we will send a new address through. So we'll run that and have a look at the pattern that we get. So you can see at our different time intervals here, so we've got at the first 4 seconds, or 4 whatever the units were, we have a 0. So our address is, it would actually have 2 trailing zeros behind this, but it's just cut it off. So it'd be 00FF00. So that's for greater than or equal to 0 through to less than or equal to 2. We've then got our greater than or equal to 3 and less than or equal to 4, giving us that would be 0000FF, and then the other giving our FF000. This is the logic diagram that we can get out of EDA Playground. And if we have a look at it as a whole, it's sort of like, whoa, what's going on there? But when we start to break it down, I can look at a logic gate here. So we've got a logical and into that I have a GE is a greater than or equal to, and LE is less than or equal to. So we're comparing either 4 or 3 to the incoming address. So we can see the address goes into all of these, and then we're ANDing the outputs together. So if I go back to the code view, so down here I've got if it's greater than or equal to 3 and less than and equal to 4, we're going to output the current color as blue. So all we're doing for each of these is one of these logical tests. So basically we've got here greater than 5, greater than and equal to 5, but less than and equal to 9. We'll follow this path. And greater than or equal to 0 or less than and equal to 2 will follow this path. So basically you can see that we have 3 logical paths going through. And if this one is true, this is a muck. So if we get a high, we're going to select, I think it's A. If we get a low, we'll select B. It may be the other way around. And that will output here. Likewise on this one, exactly the same thing. A high or a low will select the relevant input. And we've got a slightly different setup for down here. But all we're doing is passing through the color code based on these values that have been selected here with the logical ANDs. And they ultimately get passed through a latch that will come through an output and give us our 24-bit color code. Now you're probably wondering how I produce this diagram. So I'll just go back into my EDA playground, and previously we've been doing this setting here so that we're actually compiling our code and executing it for the waveform with the tick box to output the waveform. So all I did to get the other one was I chose this Yosis, and again making sure I have show diagram after run, and that instead will output this logic diagram for us. And this view is using a different software called Vivado, which is the programming tool for the Xilinx FPGA. So this is actually showing exactly how the hardware will be built on the chip. So I'll give you an overview of what's happening. We've got our addresses coming in, and they're all buffered as an input. So that's a 3-bit or 4-bit address. And then over here we have our outputs. So that's our 23, 0 to 23 output to do the color code. And in between, I'll go through these different blocks. We'll just look at this row here. These are all 4 input lookup tables, so LUT4. So if I go over to details on lookup tables, what they do is they'll take your 4 inputs, and using whatever combination you've said should give us an output, we'll get a high on here when the inputs match a certain pattern. So basically we would have a table like this, and we would say that when we have a certain pattern, if it is going to be an output high, we will get a high on here. So we're just defining this table to say, on this pattern, give me this output. So single bit output versus 4 bits input. That then goes through, I'll do the middle one first, but it basically goes through and says, okay, when this pattern matches here, I'm going to clock this flip-flop, and the D of the flip-flop is going to be a high, which will give me a high on the Q output. And if we look at what bits we're dealing with here, we've got bit 8, 9, 10, 11, 12, 13, 14, 15, and I go back to my code. So those middle bits are going to represent this value here. So you can see they're broken up to 3 lots of 8 bits. So 0 to 7, 8 to 15, and 16 through to 23. And those blocks correspond directly to these 3 different color values. So depending on what of these goes high, will decide which of these outputs we get. So this is literally just a latch. If I look up the data sheet on that one, so it's basically, we will get the value of D on the Q output if G and GE are high and clear is low. We will also get it on a low transition of G. So it's just a slightly different variation of a flip-flop. Okay, let's look at these ones that we can expand out a little bit. So again, we've got exactly the same flip-flop, but we've just got 2 3 input lookup tables to break down the different possibilities for that. So all of the gates within the FPGA are not actually AND gates, NOR gates, NOT gates. They're all lookup tables. So everything can be done just by saying, all right, when I've got this pattern of 1s and 0s, I will get a single output on a match, and that just gradually travels through the logic. So hopefully that gives you a slight bit more understanding of what's happening behind the scenes.